All right, so yesterday we introduced density curves and in particular the normal distribution. We talked about the fact that it's symmetric, unimodal, bell-shaped. It happens in a lot of real-world scenarios. And we talked in particular about the 68, 95, 99, 7 rule. So that empirical rule that tells us that 68% of all values fall within 1 standard deviation, 95% fall within 2 standard deviations, and so on. And so what we had was when we fell at those exact cutoffs. So if I was exactly 1 standard deviation above the mean, I could go ahead and calculate percentages to the left or right of that. Or if I wanted to be within 2 standard deviations, like I can calculate each of those percentages based on those specific locations. But what's going to happen in the real world is we're going to have values that don't fall on those exact cutoffs. And so while that empirical rule is a nice little shortcut that we can use when we have specific pieces of information associated with that normal distribution, there's a lot more times where we have a value we cannot work with those percentages for. And so what's going to happen here is when we work with those normal distributions, we talked about the fact that the distributions all have their own unique shape. So they're all symmetric, unimodal, bell-shaped, but the standard deviation dictates the width of the curve. And because it dictates the width, it also then dictates the height, because we said those density curves always have to have a total area of 1 underneath. So what's going to happen here, I'm going to come back to this slide here in a second, but we're going to want to calculate areas under the curve. So when we want the proportion of values that fall within a given range of values, we're looking for the area underneath. And because that total area is 1, when we calculate those areas, those are the proportion of values that actually fall within the given interval we're looking for. So what would happen is if I had to attack each normal distribution as its own unique entity, I'd have to do a lot of calculus to calculate areas under the curve. I'd have to calculate the formula for the normal distribution and a lot of advanced math that we don't need to be worrying about at this time. And so what's going to happen is we're going to take our regular normal distributions and we are going to transform them into what we call the standard normal distribution. And so the standard normal distribution is what we're going to be utilizing. It's a single normal distribution that works for any other normal distribution. So when we talked about calculating z-scores a couple lessons ago, we talked about how we transform the data. So we just take the value minus the mean, divide by the standard deviation. And what happens is if we do that with each of our normal distributions, every unique normal distribution gets transformed into this specific distribution. And so by calculating those z-scores, that's the key here. When I'm calculating those z-scores, I'm transforming the data so that instead of the unique normal distribution that I started with, I create a new normal distribution that has a mean of 0 and a standard deviation of 1. And so what that does is if I take any other distribution and calculate z-scores, it automatically transforms into the one we see on the screen here. And so that's going to have our 0 mean in the middle. We simply go 1, 2, and 3 standard deviations above the mean, 1, 2, and 3 standard deviations below the mean. And then since all of them will transform into this specific distribution, they've already calculated areas for us. So we can actually use that one single distribution, calculate the associated percentage with that z-score, and that's going to be equivalent to whatever my original information was. And so that's going to be kind of the process we're using here. So we're going to standardize the values, and then they have calculated the areas under that standard normal curve for us. So knowing that that standard normal curve is going to produce the same percentages, it's going to calculate the same area as my original distribution, it allows us to find those areas, it allows us to find those percentages much quicker, much easier, because we only have one curve to worry about now instead of each unique curve and doing all the calculus behind it. So table A, or table Z as it's sometimes referred to, is a table you're going to get in class. You'll have access to it every time in class. You have access to it on Google Classroom. But what it does is it tells us those areas. So they've calculated the areas that we're interested in. Those give us the percentages, the proportion of values that fall within a given range. But we have to make sure, and this is really important for this topic here, when we look at table A, we're looking at areas that are to the left of the z-scores we calculate. And so that's even illustrated in the graph that they show on the table. So when I look up a z-score, the table is going to tell me what area, what proportion of values are less than or left of that particular point. So if I want to calculate different kinds of intervals, so if I want to go between two values or if I want to go to the right, okay, I'm going to have to manipulate the value I get from the table to adjust for the area that I actually want. And we'll talk about that process here. So as I look at table A, some things to note here. We've got our z-scores is what we're talking about. So we calculate a z-score, we use it to find the appropriate area on the table. So the start of my z-score is going to be on this left column. So there's a positive side and a negative side to the table. So in this case, we're illustrating the negative side. But I look for the start of my z-score on that left column, and then along the top gives me the hundredths place. So every z-score I calculate, we're going to round to 2 decimal places. And then what's going to happen is I'm going to use those z-score values to then determine the area under the curve. So these little decimals that we see throughout the middle of the table, those tell us how much area, what proportion of values would be less than or left of that particular z-score. And then whatever proportion is associated with that z-score goes back to our original context. It's the same percent of observations that would be less than the particular value that I had in question to begin with. And so what's going to happen here is when we use this table, so if I'm looking for the proportion of observations that are less than 1.4, so I locate 1.4 on the left column. Since it's 1.40, it's not stated there, but if I have the 0 hundredths place, I look for the 0.00 on the top. And then where those two intersect is what I'm actually interested in here, which would be that 0.9192. And so what this table is telling us is that 91.9% of values are left of that 1.40 standard deviations above the mean. So that's the type of thing that we're going to be looking for, is what area is associated with our particular cutoff score. When I want to go the opposite direction though, so if I want to find values that are in this case greater than my z-score, so greater than negative 2.15, I start by locating the negative 2.1 on the left, the 0.05 on the top, and then when I put those together, we get an area of 0.0158. Now the problem is that 0.0158 tells me that 1.5% of values are less than negative 2.15, but we wanted values to the right. And so this goes back to that idea with density curves that the total area is equal to 1. So I'm going to take that 0.0158, I'm going to subtract that number from 1 to get the actual area remaining to the right of that point. So when we're using this table, we find the values to the left, and if that's what we're looking for, we just take the value and interpret it. If we're going to the right, then we need to make sure that we take that value we find in the table and subtract from 1 to get the value that we actually want. So I can calculate both areas, it's just that the table is going to give me specifically to the left, and then if I want to get to the right, I have to subtract from 1 to find the appropriate percentage. So as far as the steps are concerned then, when we're running this type of normal distribution problem, we state the problem, meaning when I write out what my distribution looks like. So normal, whatever the mean and standard deviation are, I put in for the parameters. And then they're going to give me a value or values to evaluate. And so we're going to tell us that X has to be less than or possibly greater than, or we could also have something where we want X to be in between two values. So we're going to state all of that to begin with. So I have this normal distribution with this mean and standard deviation. I'm looking at this particular value. I want to be less than, I want to be greater than, or I want to be in between those two values. So we always start with that. Then we're going to take that X value or values, and we're going to calculate the z-score using that information we just discussed. So what's going to happen here is I'm going to take whatever X value there was, and I'm going to plug it into my equation, and I'm going to calculate the appropriate z-score. Once I have that z-score, I'm going to sketch my distribution. So I'm going to draw my normal curve. We're doing the z-score, meaning the normal or standard normal curve, so 0, 1, 2, and 3 in either direction. And then whatever z-score I calculated, I find that location on the x-axis here, and then I shade whichever direction I was trying to go. So if I wanted to go to the left, I would shade everything to the left. So then what this does for me is it allows me to see ahead of time kind of what percentage I should be looking for. So I have an idea in my head what type of value I should be looking at. So it kind of helps me remember if I need to subtract from 1 to make sure that that makes sense with my picture, then I have that accounted for. Once I have the distribution drawn, then I go to calculate my percentage. So I can use table A, and I take that z-score, whatever it happened to be, and I convert it to a proportion or a percentage. So the percentage to the left, percentage to the right, or in between, depending on what I'm looking for. And then the last thing is making sure that we state the results. We actually interpret the values. So once I find that final proportion, what does it mean in the context of the problem? So this percent of values were less than this particular cutoff, or this percent of values were more than, whatever the case may be. So we're going to follow those steps every time, which means every normal distribution, we have what we're stating, what values we're working with, calculate the z-score, always draw a sketch of the distribution with the appropriate area shaded, and then convert that z-score into a percentage using that table. So as a quick example here, we're talking about cholesterol in the blood. And so high cholesterol levels may increase the risk of heart disease. So they're saying that in this particular instance, the cholesterol levels are roughly normal within a given population. They have a mean of 170 and a standard deviation of 30 milligrams per deciliter. And we're interested in values that are above 240 milligrams per deciliter. So we're looking for all this information in the problem. So the question is, what percent of people have more than 240 milligrams per deciliter of cholesterol? So when we state the problem, we state that we have a normal distribution, give the appropriate mean and standard deviation, and we state the interval we're looking for. So in this case, we want X to be larger than 240. So then I can take that value, I can convert it to a z-score by plugging it into that formula. And so when I get the formula, the z-score, right, we're looking to the right, so z has to be greater than 2.33. I take that value and I use it to sketch my distribution. So I sketch the normal curve. I mark where 2.33 would be. I'm shading everything to the right, so that means when I find my answer, it should be a really small percentage. And then I look the value up on table A. Now when I do this, okay, this first part of the statement, they're saying when I look up 2.33, I get this percent. So 99.01% of all values fall left of that 2.33 cutoff. So 99% of the people in my population would have a cholesterol level less than 240 milligrams per deciliter, but that's not what they asked me for. I want to know what percent have more. So that's where that 1 minus is going to come into play here. So if I subtract from 1, I get my final answer that I can then interpret in context, where it's about 1% of boys have a cholesterol above 240 milligrams per deciliter. And when you state the context, don't try to reinvent the wheel with this. Just restate their question with the appropriate percentage inserted. So it says, what percent of people have more than 240 milligrams per deciliter? So our answer is about 1% have cholesterol above 240. Okay. Real quick then, if I want to do like an interval in between, so what percent of values are between 170 and 240? So same normal distribution. I don't have to restate that part of this, but I do want to make sure I state the values that I'm changing to. So I want to be between 170 and 240. So I'm going to convert both values into z-scores. And so when I calculate the two z-scores, I get my 0 for the lower bound, 2.33 for the upper bound. I want my z-score, I want my percentage to be in between. So this time, when I look those values up, so after I sketch my distribution, find the 2.33, find the 0, we're shading everything in between. So I know about half of my distribution should be within that interval. And so when I look the values up, what's going to happen here is I get my area for 2.33, the 0.9901. I get my area for 0. And what's happening is when I look up that table, that first percentage was everything left of that 2.33. And then the second value, the 0.50, is everything left of the mean. So I don't want all of the green. I want none of the red. So I'm going to take those two values and I'm going to subtract them from one another, and I get the value that I actually want in between, or in this case, 0.49. So then in the end, we interpret. So about 49% of boys have cholesterol levels between 170 and 240 milligrams per deciliter. So it's the same process every time, where we state the problem and values we're looking at, convert those values to z-scores, sketch the distribution so we have an idea of what we're looking at, and then using table A, find the appropriate percentage, and then if I have to manipulate that percentage, subtracting from one or subtracting the values from each other, then I get that get my approximate proportion. So with that, you should be able to attack the problems for today. And so as you're working through these, if you have questions, obviously you have the answer key online, or you can ask questions in class as we move forward with these normal distribution calculations.